All right, so it's 11:15, sorry. Ready for the day to be over. Zooming ahead. So welcome to the ECM seminar for today. We're really delighted to have Todd Murphey here. He's at Northwestern over in mechanical engineering, and I know him because he and I are both in this area of data-driven methods development, but he works on cool robotics problems, much cooler than I do. We also have a bit of a shared love of the data-driven methods from both the application and the mathematical perspective. So Todd got his undergraduate degree in math. So I think he said to me, I'm a mathematician at heart, maybe at some point. Maybe
yeah, I'll say something about that.
Something about okay. And then he went on to do a PhD in control and dynamical systems at Caltech. Since then, he has been doing all sorts of cool things with robots that I will let tell you about.
All right. So I'm going to be talking about embodied learning, and I think it's true. My undergraduate was in math. My PhD was in control and dynamical systems, sort of a mathy topic. But I'm actually not a mathematician, and I'm not a mathematician. And the goal of this talk is not to tell you all how to be mathematicians. The goal of this talk is more about, I think that there's a set of really important roles that mathematics and theorem proving and good structures of proofs versus less good structures of proofs play when we're dealing with new ideas and thinking about how society is going to rely on technology that we're developing. And so I don't want you to dwell on this too much, but it's worth thinking about, like, how much when you get on a plane and fly someplace, like, how much does that process depend on math? And there's a bunch of ways in which it doesn't depend on math, but your willingness to get on a plane actually is deeply connected to mathematical techniques, proofs about the correctness of those techniques, and whether or not you really think that the planes are reliable enough for you to be willing to think that they're safe. And that when we talk about AI, I feel like there's a huge discussion happening nationally right now about reliable AI or responsible AI or explainable AI, and that tends to be discussed in the context of qualitative features rather than properties. And so the main thing I'm going to be talking about today is I'm going to talk about, like, the type of work that my group does, and I'm going to, at each stage, attempt to connect that to the way that we think about properties, the way that we use mathematical properties to motivate even, like, mechanical design changes in what we do, something not necessarily very mathematical in its own right. And then think about, like, what are the longer term opportunities, maybe for mathematicians, but also for engineers, for, like, really using math more in a learning driven context. Because I think right now a lot of people in robotics and a lot of people in lots of fields just sort of see this tsunami of AI and ML techniques doing stuff. It's not totally clear what it's doing, but it is clear that it's doing stuff. And being too cynical about that is also not healthy. To sort of ignore the fact that, in fact, Google and Meta and all these places, they are doing real things that were not possible before. And then the question is, well, what do we do in response to that? Should we be trying to just constantly trail them? That's probably not great. Like, what is our role in this? So I think a lot about embodied learning. I'm going to talk about even what that phrase should mean. This is just my attitude. Embodied learning, embodied intelligence, embodied computation. Like, people use these phrases, everyone means different stuff. I mean it in the context of experiments. So for someone who cares a lot about math, I do probably more hardware, and hardware that is closer to sort of real applications than most people who spent parts of their careers proving theorems. We do a lot of work with robots that help people interact with tasks. We do work with physicists on emergent behavior in mechanical systems. We've done work up here, upper middle, on social navigation, where robots have to reason about an unknown number of people with unknown preferences. making decisions in an environment that's pretty unstructured. And we've also done other work like here. This middle bottom was a project where robots are supposed to be exploring an urban environment. This was a hardware experiment field test that was set up by DARPA. Like all these things have certain properties in common with each other, but importantly, all of them depend on some form of learning in a real way. They're working in unstructured environments. Actually, the emergent behavior one is a little more subtle than learning per se. But the others all are operating in unstructured environments. And the social navigation is one that's really worth thinking about, because not only is the environment unstructured, but to the robot, people are profoundly unstructured, right? And engineers want people to be modelable. And the question is, like, should a robot operating around people think of them as modelable or think of them as unknowable? And if we think of them as unknowable, what can the robot do in response to that framing of the problem it's facing? So now this comes down to my background as in control. So of course, I use a background in control theory as my lever for everything. That doesn't mean that control is like the only thing or the right thing to do. It means that it's the thing that I understand the best. And why does learning need control? Well, robots need to learn for a bunch of different reasons, but what can you assume? Oftentimes you don't get to assume really important axiomatic starting points of learning. You don't get to assume that the robot has data that represents the environment ahead of time. In fact, for robots out in the environment, most of the scenarios that I just showed you, there won't be data ahead of time. There's only the data that the robot experiences as it interacts with the environment. So also learning in that regard often is single shot. So this phrase shows up in the machine learning community. The idea is that you do not get to have multiple attempts at learning about an environment. There are real applications where, like, whatever you're doing, you have to learn that. You have to use your one body to learn how to do something or learn how to have an interaction.
So does the robot not have kind of processed data that the people that created it used to kind of?
Yeah, so it might have some data, but I think in general, this is a disingenuous representation of the problems that the robot faces. So even if it has data, a reasonable question is whether, given the data it has, is it better off using that data as a prior, or is it better off just re-regressing the world? And there are lots of settings where it is better to ignore all of your prior data and just re-regress the world based on the data that you collect. And so even though there might be settings where you have data ahead of time.
I was not thinking in terms of data, but kind of you program the robot with some set of rules.
With some set of symbolic logic that the robot has to follow.
Which actually were the result of data.
Okay,
so there is kind of synthesized knowledge that you put in.
A lot of what I'm going to be talking about today is, most of the time, this is why I talk about the robot knows something, right? The robot has some starting point, and then oftentimes everything about what it doesn't know flows from that grounding of what it does know. And actually, one of my interests is understanding, what do you do when that isn't true? When the robot is actually not allowed to know anything from its starting point, like, do you still have a well-posed learning problem that is manageable for the robot? Nevertheless, you're totally right. There are settings where the robot, most settings and applications right now, start with assumptions that there are some set of knowns and there's some set of unknowns, and the learning problem is to model the unknowns. Obviously, like, extending this really, really far becomes a philosophical problem about, like, what does it mean to know something? I'm assuming that at the end of the day, we're talking about you have a model that the robot has to execute. And that if it doesn't have that model that it can execute to make predictions, it's an unknown. Okay, so this whole sort of idea, by the way, like, it's already clear we are not going to make it through this whole talk. It's split into 3 sections. And as you ask questions, I'm going to actually want to engage about them. The last section is about a really, really well formalized mathematical area of machine learning that is worth knowing about. I'll at least comment on it, but it's also worth knowing that the better formalized things are, in general, the less well they work, which is why I'm bringing it up. But so I'm going to sort of adapt as necessary. Most robots roughly work in this sort of framework. They collect measurements. If you were talking about a robot whose purpose is to learn, it's going to generate some sort of information measure that's going to allow it to reason about what it does know and what it doesn't know. Then it's going to update its representation generically. This might be like a deep neural network. It also might be an architecture of symbolically related neural networks. Some of those things might be predetermined by the program. It's going to then take, it's going to plan based on the state of the representation. It's going to plan actions and it's going to execute those actions, collect more data as a consequence. And this thing being a closed loop system is actually different than just regressing over data and then using that as a model of both the world and how you make decisions about the world. And this goes all the way back to the 1930s and Bodie figuring out that the right way to regulate op amps is in a closed loop architecture rather than in an open loop architecture. Like this is sort of, as an idea in engineering, this has a 100-year history. And I'm trying to think about how to make that idea make sense in the context of learning. So this is really not so much for you, but this has to do with a cultural divide in robotics. That right now, overwhelmingly, when people think about control and learning, what they mean by that is that you have a control system, you have a block diagram that describes the control system, and that the thing that is unknown is how you're going to control it. And so historically, we have things like optimal control where we specify objective functions and blah, blah, blah. We're really good at all that. And then people say, no, all that stuff is nonsense. You just need a simulator of some type, and I'm going to learn a neural network that tells you what my action profile should be. Control for learning, from my perspective, is the opposite. That now the uncertainty is all in the dynamics of the learning process itself. And that what we want is to synthesize a motor control strategy that allows us to adapt to the state of whatever that learning process is. It's totally fine to think of this as an unknown deep neural network. And that you know that thing is unknown, and what you want to do is take actions that regulate its evolution. And so then the question is, well, should that control thing be something that you write down explicit formulas for, or should that control thing be itself something that you learn? And so, I'm happy for there to be learning piled on learning. That just starts to seem so complicated to me that I don't know how to reason about it. And so in my lab, we tend to focus on things where we can actually write down exact mathematical statements about the principle for that control block. And then this is where, so in machine learning, machine learning is sort of the taking and processing of data for prediction. Reinforcement learning, which I will discuss briefly as well, is the processing of models for decision making. These are not the same thing. And what I just said, you can frame it as a reinforcement learning where you have a learner on top of a process, and part of that process is itself a learning goal. But they aren't the same thing. Both of these things right now are sort of enabled by big data. And it's worth thinking about why big data plays such a role, but there are a couple of exceptions. I know a few people here work on neural radiance models, so NERF models. And these NERF models, part of what's astonishing about them is that you can learn a neural network representation of an environment with, a few images effectively, like 10 images can be sufficient. So not everything is driven by big data. The other thing that's just worth noting is that this data really importantly comes from people. And most of you in the crowd, I think, are not engineers. You were not trained as engineers, but like when I was in graduate school, vision was not the sensing modality that everyone used. Ultrasound range sensors and things like that. Those were the things that were used. The thing that happened was not just the availability of images, it was the availability of people labeling those images. That completely changed how we think about the collection of data, because we have billions of images labeled by billions of people. It's just like, from a data set perspective, it's amazing. And it's worth thinking about the downside of that, by the way, which I'm also going to talk about, which is that maybe the type of stuff that we're talking about in this talk isn't so affected when you really do have that big data. But there's lots of sensors that are relevant to robots where there's no way you can label them. Touch sensors. We can't label touch sensors because we can't render touch, right? Like however this feels, maybe you can get someone to kind of recognize it when you're generating a haptic interface. You cannot get it well enough for them to label that surface. Same thing with ultrasound, or same thing, like there are lots of physical sensors that we have no labels for, and we will not ever have labels for. This, I think, is a good example of, we might want to have this structure ahead of time, but there are real sensor characteristics of real robots that will never have that structure given to it ahead of time. I don't want to focus on this too much. What I love is this quote. So this is from 2023. The state of art around data collection is very, very immature. This is the thing, this is the phrase that I want to resonate. That even as we get really, really good at given a data set, regressing increasingly large data sets into increasingly useful tools, how we obtain that data is not something that's done in any sort of principled way. It's just whatever data we happen to have. And this is something that automation could potentially solve. Question. I can tell. Yeah.
Yeah, it's funny that you are talking about these things, but you are not using the terms that I would use, which is measurement theory, right? When you are talking about, can we measure the feeling of touch, right? Yeah. It's like anything is that there is a quantity, there is a proxy that is actually giving you something. And those processes, for some things, we have developed them for a long, long time, right? To get something, maybe you can get the Fourier decomposition of it, and now you know what frequencies are there. But temperature, right? You look at something expanding, but for some things, we have not developed them. And for other things, we have actually not truly developed them, but we accept them to be reasonable. Like people labeling something is a measurement process.
Yes,
right?
Absolutely.
And it's kind of, when you think about measurement processes, there are ways to measure how reliable they are, how all of these things. And in many of these cases, we have made assumptions that human labeling is reliable and trustworthy and comparable. But in many cases, we don't know that, right? And there are things in which, so I think that, again, engineers also don't learn very much about measurement theory, right? People in psychology that do psychometrics worry much more and learn much more about measurement theory than we do. And it would be helpful for us to know more about that, so we actually make more sense of this process.
Yeah, and by the way, complete ringer in the crowd, and I'll pay you $100 later. A lot of what I'm going to be talking about is, what do you do when you know you want to measure something and you also know that you have no model of that measurement ahead of time? That there has to be still something that tells you, I'm currently in the business of learning. And I'm going to give some hardware examples of what that looks like and where there's still some outside instruction that matters to the process that you're governing. Okay, so this is just my cartoon. We've got a spectrum going from no data to big data. And that, all of the stuff that's been happening for the past 3 years or so is really, really rich. It's on that right-hand side. But as you get leaner, a lot of this is characterized in terms of like making the current technologies of these generative models less data dependent. But there's not very much that assumes I'm going to start with no data and no model, and then I'm going to ask, how do I act in response to that reality? And so here, let's say that I started with a physical model that I know is wrong. I start with, like, say, some sort of potential energy-based model of a near-field sensor has electromagnetic interference as its primary sensing modality. That's a pretty standard thing that we build, and it's also something that happens in nature. So there are ways of getting a first model for that, but you also know that they're wrong in a bunch of important ways. You know that there's no way that model is going to continue being the right way to reason about the world. And so then you might be in the business of adapting the model from wherever you started. You also might say, nope, I have something where I have no idea what the sensor is. And in either case, you're going to have some way of sort of bootstrapping your behavior so that you're not in equilibrium. Because actually the worst thing for learning is equilibrium. Which is kind of weird because everything else in engineering analysis tends to want to take systems from out of equilibrium and push them into equilibrium. That's what like lots of analysis is aimed at. So challenges. Let's say that you have non-traditional sensors. You have MRIs, you have atomic force microscopy, electrosense, tactile. These depend on more on underlying physics than vision does. Vision is largely ray tracing at these days. Does a really good job. It's one of the reasons we use it. Importantly, many of these physical interactions just can't be simulated. You can try to simulate them. You might get something qualitatively helpful, but you're not going to get a predictive model of the thing that you care about for lots of interesting phenomena. Also, data for physical systems has this weird property when you think about it in time that oftentimes sensors are not changing their states very quickly. That instead there are events that you have to be responsive to, and that in between events, there's very little to regress. This is different than the internet, right? Like the internet, for better or worse, is just a big gob of data. You do with it whatever you can. Whereas here, the sort of temporal distribution of how you encounter data means that sometimes you regress it and sometimes you don't. You have to make decisions about that. Also, if you're going to use that closed loop diagram that I showed, if you're going to have a closed loop system that is responsive to the learning, it's going to have to be synchronous with your motor control. So that, like, think about this for a second. If that learner is not changing its state, there's nothing for my actions to respond to. And so one of the things that we've done in my lab is that we have server stacks that are busy regressing deep neural networks in real time as a robot interacts with its environment. Honey's going to rely more and more. This is just becoming accepted. When you think about getting on a plane where the entire plane design, the flight control and everything was designed by an AI system. And like, what would make you feel okay about that? I think is a super complicated question. And then lastly, I want to just point out something that this gets shockingly ignored in the machine learning literature. That underlying every major machine learning technique that you've ever encountered, there is an assumption that the data that you are using to regress the model is independent and identically distributed relative to the distribution that it's drawn from. This phrase is important for two reasons. One is that it is like buried in the beginning of every theorem assumption that you encounter about any machine learning process that I've seen that actually works. And then two, embodied systems cannot produce IID data. It's impossible. Because as a body moves around continuously in time and space, the temporal correlations break the IID property. And so this is now like where we are at something that should like just kind of give us all knots in our stomachs from my perspective. That on the one hand, we are 100% relying on these technologies. On the other hand, we know that at an axiomatic level, we cannot meet the requirements of the algorithms that process the data for us. And so the question is not, well, I'm going to give up on learning. Right? Which for a while, by the way, I was super cynical about learning and then eventually had to figure out how to not be cynical about learning. And instead, we should be asking, what can embodied systems do? A lot of data collection looks like this. Sadly, so the Flight 370 Malaysian Air crash in the South Pacific. Well, how did we search for debris? We put robots on the bottom of the ocean and we just zigzagged back and forth, hoping that we would encounter debris. Noteworthy because it's how we search for data anytime we are prescribing an algorithm to do it. Also noteworthy because like it is not ever what animals do. I'm not a big bio-inspired anything. Like I like to have mathematical descriptions for everything that we do. Nevertheless, that picture on the right is much more what an animal might do when it's searching for something. And we can ask the question, why? And is there a principled explanation for the difference between raster scanning on the left and this curvy looking weirdness on the right? So to take away from this, if you're collecting data, scanning is somehow a easy to implement, but fundamentally broken idea. And how do we characterize that in terms of a mathematical description? The way that we do it is going to be to characterize the needs of the data collection in terms of a particular property called ergodicity. It is not the only way to do this, but it's the one that I understand the best in terms of its relationship to properties like IID. So how do we think about information as it is distributed through an environment? There's a few choices here. The thing that overwhelmingly gets used in practice is Fisher information. And so even when you find yourself using Fisher information, which just says, in the environment, I'm looking for parts of the environment where things change faster rather than things that change more slowly. Like that is the idea of Fisher information. And it is, what's good about it is that it really applies to the vast majority of situations, particularly when you're getting started. It is not particularly good at refining models, but it's really, really good at looking for opportunities to learn when you start out with like no knowledge about the environment as well. Also, Fisher information, because it only involves derivatives, it tends to be easier to work with when we're talking about like neural network architectures, anything that's really high dimensional. We often want to work with it because it's just like computationally more manageable. If you're not working with Fisher information, entropy is the thing that overwhelmingly is sort of the most right thing to do. It says, what is largely the most common representation of entropy says, given my current model, how much does my current model encode about the world as I've observed it? And what you're trying to do is look for, in the environment that you're in, you're trying to look for opportunities to collect data that will improve, that is in entropy-rich regions. Both of these are fine things to use. We use them both all the time. The important thing is that they both are metrics that one can then think about optimization techniques for. And then this last thing is maybe the least intuitive bit, which is that maximizing either of these terms does not buy you what you think it should buy you. Because maximizing information will, like if you think of any given distribution of information across an environment, if you maximize that quantity, you're going to go someplace, which is fine, and then you're going to stay there, which is not fine. Because staying there violates the IID property exquisitely, right? It's like the worst possible thing you can do. And so what you need is something that, what's wrong here is that maximizing information has equilibria. Like you need some approach that is effectively guaranteed to never give you an equilibrium solution in the sense of like your dynamic states over time. So what do we do? And this is where the relationship between entropy and ergodicity starts to matter. So ergodicity, by the way, Shannon talks about it in his first paper about information theory. Like ergodicity in that paper is on equal footing with the idea of entropy. But for a variety of reasons, ergodicity is not so relevant to like communication channels generically. Instead, ergodicity is sort of like a way of thinking about encryption, which we don't always worry about when we're thinking about communication. So ergodicity is in that regard in applications for a long time. It sort of receded into a supporting role. But for us, the difference between ergodicity and entropy is that if you have an entropy field, so these level sets describe how much information there is as a function of the geography of your operational space, that your information maximization strategy is going to say, I'm going to go here, I'm going to have these correlated states, which already make me unhappy, by the way. You're going to have these correlated observations, and then when I get here, I'm going to basically stay there, which is going to break a lot of the important starting points for regressing data. Ergodicity says, I'm going to go and I'm going to care about the states that have higher information content, but I'm also going to care about, so I'm going to weight every state in the environment according to its information value. And here, the thing that is worth thinking about is we still have temporal correlations. Cannot get rid of them. But if I think about a very short duration, those correlations are going to be higher. If I think about an even longer duration, if I keep them in order, they will still be higher. But this is never the way machine learning algorithms work. Machine learning algorithms take a subset of data, they randomize it so that you break those just through ordering. And as this trajectory gets longer and longer and longer, the batch of data that I've collected becomes increasingly decorrelated. Right, so asymptotically, ergodicity gives you IID properties. So suddenly now we have a relationship between our ability to manage the temporal evolution of an embodied system and get it to at least asymptotically agree with the axiomatic starting point that these machine learning algorithms require. This was not how we thought about ergodicity 15 years ago. Like in my group, it was more this sort of like vague intuition that this was really important. We were working with biologists who were interested in explaining animal behavior. When I looked at it, I happened to be reading lots of papers about ergodicity, and I became convinced that this was a better way of explaining animal behavior. It's only now that we can start to like say precisely why these sorts of trajectories might be generating better data for purpose of learning.
I'm not sure I'm wrapping my mind around it the correct way. It's on the right side, when you have this information distributed, so wouldn't that information distribution change once you've learned something?
Yeah,
I mean, once you are there,
Yes.
then exploring right next to it, probably there's not much information to be gotten anymore.
That's a good, that's a really good point. It changes. So first of all, there's sort of two things here. One of them is on this right side. When I talk about learning updates that are synchronous with your planner, they could be synchronous at every time step, literally. They could be synchronous across batches of data collection, where I know that I know that it's going to take me 1/10 of a second before I get my next update, and then I'm going to plan for that 1/10 of a second independently and then regress. I could also purposefully allow the updates for my learning model to be longer than that. This is actually practically what people do in almost all machine learning when they use batches of data instead of single data. Now, to the substance of your point, there's both good and bad things that happen when these level sets are evolving in real time. The good thing is that, these level sets are changing, and where that maximizer is changing accordingly. The bad thing is that where that maximizer is changing is generally not very much. It's a continuous process. So you're going to get like a little sort of squiggly neighborhood around that maximizer on a time horizon that's relevant to this trajectory. That's not worth being worried about. It's breaking the IID property, still annoying. That by itself is not the biggest problem. The bigger problem is that this trajectory has ignored this set of features. And if you allow this process to just run unmitigated, what will happen is that all of the information that you originally estimated is going to decay. You should think of this as like, so we have robots that look at toys. I'll show them in a second. But when you have multiple toys, if you're information maximizing, what will happen is that from the far field view, you'll notice the toy that has more visual features. Because that has more visual features, the amount of information will be higher over that toy than it is over the other toy. You'll zoom in on it, and then the learning model will literally forget that the other toy existed. The information density will start to only be around the original toy, and the other one will degrade. When I talk to funding agencies about this, I talk about the difference between information gathering if you're the fox versus information gathering if you're the rabbit. The fox may have a good reason for only caring about one set of features at a time, in which case just information maximizing might be a good strategy. The rabbit cares about all foxes, right? Like the rabbit is constantly in the business of being aware of the entire environment and can't really afford this forgetting phenomenon that happens pretty easily.
That in a sense is also related to shortcut learning, right? That you go to one thing and maybe in some cases you go to the easier one.
Yeah.
That actually.
So, robots actually lots of algorithms during learning processes tend to focus on one thing to the exclusion of everything else. Yep. So the focusing on one thing early in the time horizon, there's nothing wrong with that. That's a desirable property. Honestly, you don't want to be constantly changing attention. The longer the time horizons, the more it matters. Okay, so you can model this in a bunch of ways. The easiest way to understand it and the shortest path to thinking about this in a mathematically completely defensible way is to say, I need to be able to compare the points in my trajectory, delta functions in my trajectory that I'm producing when I execute a control path to the information density, which is a distribution over the space. Now, I need some meaningful way to compare that. Sobolev theory is the sort of standard way that those comparisons get made. The Fourier transform is the standard way of decomposing a Sobolev space that like engineers know about. Everyone who sees this chart asks me if you can do it with wavelets. It seems like you should be able to do it with wavelets, but we have never been able to make that work. The important thing for us is that when you have a trajectory, you can actually evaluate the Fourier decomposition of a trajectory very easily. It's actually just a dynamical system that evolves in time. The Fourier coefficients themselves are a dynamical system that evolves in time. And the information density, that also has a Fourier decomposition. And then the measure that you're optimizing is the measure of comparisons between Fourier coefficients. So what this does is it creates a differentiable, well-posed optimization. And what my group did in this area was that we used this distance from ergodicity along with a regularization term, a control effort. And it turns out that you can like formulate an optimal control problem that has numerical solutions that are easy to work with. A little bit of history about that. The first time we did this, it took about a week to do the computation for roughly the planar system that I just showed you. And now we do the same calculations in like a 10,000th of a second through lots of numerical tricks that we've learned over the course of a decade. This is the way I would recommend thinking about it mathematically. Infinite dimensional space of distributions, treating your trajectory as a distribution of delta functions, and then decomposing them into a common space where they can be connected. And one of the first things that we did was we looked at, well, given the physics of an electric fish that's able to emit electromagnetic waves and able to detect the change in voltages on its skin, can we make predictions about how it would localize an underwater conductor? There's no learning going on here, except that the fish is using its motion to determine the unknown parameters of the conductor's position. So, it's learning, but it's learning a 2-parameter state. And the only thing, this is what we get from synthesizing our trajectory while updating that model every time step. And my claim is that just like raster scanning, by the way, fails in this problem because of the physics of the sensor. And would you want to guess this trajectory? Like, it's not a random walk, but it has the characteristics of randomness that one needs in order to make this conductor isolation problem solvable based on data collection. And now what I want to now sort of turn to what is still a remedial version of learning, but it's like something that has all the hallmarks of modern learning. Conditional variational autoencoders are the simplest version of unsupervised learning. They take whatever data you're collecting, say images, they compress it into a latent representation. You don't define anything about that latent representation. That's the sense in which it's unsupervised. And then they decode it into a prediction, and you regress that model based on minimizing the error between what you see and what you predict. It's very sensible architecture. The most important thing about this is that in here you are both predicting the characteristics of the latent vectors. You're also predicting the normal distributions over those vectors in the latent space. So the latent space has normal structure that the sensing probably does not have. And for what I'm talking about now, what I care about here is that there's no human intervention. Once you've defined this architecture, which is a type of knowledge, right? Once you've defined that this is what you mean by learning, now we can ask questions like, given a robot that has this model of the world, which just takes inputs and outputs and tries to create a latent representation, what can we do for the robot making decisions about how to do it? And so we're going to interpret, not that ergodic coverage provides IID guarantees. It provides as close to IID as you can get. This is the sort of better version of the idea. We have other results on what are algorithms that create as much IID goodness as possible. There's a couple of different ways of thinking about that. One of them is ergodicity. That's well accepted in some communities. The other one, which will sound familiar, is diffusion. So the closer you are to being an exact diffusion process, the closer you are to generating the most IID data that you can generate. And we've used both of those ideas in different settings. But the key thing is that you can, if you know that you have ergodic coverage, you can use that so that now you know you're in the business of creating data that is as IID as you can. Now you're going to look at your latent space. You want to have your latent space be as useful as possible. So you look at how many active units there are in the latent space. That means weights that are bounded away from zero. And then you have these different terms. You have the end-to-end reconstruction loss. You have a term that looks at the latent space regularization. And then you have a conditional reconstruction loss. The conditional part says that I don't just care about the average of how good I am at reconstructing images across the entire space. I also want to know that when I'm at any particular location in the world, I'm actually pretty good at that particular place as well. And interestingly, you have to do a bunch of math to even realize that this term is independent of the end-to-end reconstruction loss. That they seem like they're related to each other, and they are sort of, but as soon as you add that term, you start getting like much better models of an environment. And to give you a sense of what that looks like, so we spend a lot of time with robots looking at ducks. And here what you're looking at is the robot has this is obviously all in simulation, the robot has an unknown sensor. So it has no idea that the sensor has an array, that there are pixels. It just knows that there's an enormous vector that it experiences as a function of time. And it knows that it's in an environment that it's expected to learn in. That's all it gets to know. Oh, sorry, no, third thing, it knows its own dynamics in that environment. You can formulate this problem so it doesn't need to know its own dynamics, but it makes it much harder. So for us, the things that are known is it really does know how to move, but it doesn't know anything about the physics of the sensor, and it doesn't know anything about the interaction between that sensor and the environment. And looking at this again, the thing that is driving its motion is that on the left, it's computing the entropy, it's moving accordingly, and notice that the rubber duck primarily spends time at the edges of the field of view. This is exactly the right thing to do. Because where is it hardest to make predictions about rubber duckness is when you don't get to see all of it. Actually, the rubber duck in the middle of the field of view is very easy to make predictions about. Very little data is required to regress that. But at the edges, you have to cut off all of those features in a geometrically correct way. That requires a lot more data, and the entropy correctly captures that need for data along the edges of the field of view. Also, notice that the prediction has both features of the duck, but it also knows about the position of the duck. This was super hard to understand what was happening because it had never occurred to us that the idea of the position of the duck in the field of view was itself a latent part of the duck's representation. The idea that something is an object is different than something that does not have coordinate locations. And so these models, these latent representations are exceptionally hard to interpret if you actually don't build in that structure ahead of time.
So the thing that the sensor is learning is if I'm pointing the camera in this direction, I'm guessing what I'm seeing. And what I'm seeing is a cut off image of the duck.
Yep.
And sorry if I'm repeating, I'm trying to repeat what you just said to make sure that I understood. And so because it wants to maximize its own learning, it sees that where it makes the most errors is when the duck is sliced.
Yes, that's right.
So that's why it keeps moving in such a way that it would see the duck there.
Yeah.
So, okay.
Well, and one way to think about this is in the latent representation, the original latent vectors could be things like color, coordinate location, color, and blob size.
Mm-hmm.
Like blob size is going to be super useful at first, but blob size is going to be totally misleading when you get to the edge of the field of view. And so suddenly that latent vector has to be redefined in important ways. and it has to be re-regressed. And so eventually that blob size latent part should disappear.
Yeah, it has to learn more about the subtleties in the image of the duck to know. Yeah,
it's easy to think about the learning process as constantly adding to your model, but part of what you're doing, which is more related to the way the information theory people think about it, is you're actually also trying to surprise your model, right? You're trying to find things that negate the structure of your model so that you can then fix it with a more refined model.
So what would it make stop? Would it realize at some point that, I mean, this is a duck, it's a rubber duck, right?
Yeah.
There is so much that you can learn about
There
the
is,
rubber duck.
right, there's...
Right? And so at some point it was just like, okay, give me something else.
Yeah, actually, so let's see.
You can also ignore my question.
No. So what I've realized is we're only going to talk about perception. We're not actually going to talk about reinforcement learning or Koopman operators. I'll gloss past those things. That's fine though. It's here. So we were specifically interested in what happens when there are multiple objects in the environment. So it's not quite the same thing as saying, no, I'm done with the environment. Because the environment, like if the robot has to learn what the environment is, like what constitutes the bounds of the environment, things like that, and say, no, I've learned everything that is learnable, that is a very hard problem to solve. I would say that this idea that you have someone who is sending the robot a ping, you are learning, that's your task, and someone who in a supervised way also says, great, like you're done learning or you're going to learn something over here, right? Like that is a very, very low bandwidth type of supervision, but it's still supervision. We don't know how to solve that. What we do know is that if you put what we were originally imagining is that we have a table, we have a cluttered desk with a bunch of crap on it, and the robot doesn't get to know about any of it ahead of time. It's going to interact with it for a while, and it's going to come out of it with a model of everything. That was the sort of goal that we wanted. It can't enumerate anything. It doesn't have priors based on ImageNet or anything. It has to do everything from scratch. What we got to was ducks and plants, and but multiple ducks and plants. And here, so what you should be sort of imagining is that as it moves, it's representing entropy over the entire domain. So one of the advantages of ergodicity is that it will eventually visit, on a long enough time horizon, it will visit every voxel in the space that it inhabits. And so if it didn't see the plant up front, it'll see the plant later on. And so what happens is that it ends up sort of orbiting between the different things that are interesting. And at some point, there's probably like a convergence test in the entropy space that would tell it that it should stop. That would be my heuristic. And importantly here, it learned 4 descriptions of the environment. It learned about a duck. Doesn't know it's a duck, it labeled it A. It learned about a plant, it labeled it B. It also learned about C and D, and it learned about C and D because both of them don't have coordinates. They are both the blank areas of the environment, or like that, at least that's what we think is true. It's a little hard to interpret, but it very clearly, here it had no idea how many things it was trying to produce, and it very clearly produces 4 regressed models of the environment. One that corresponds to duck, one that corresponds to plant, and one that corresponds, we think, to the 2 blank areas. For sure, it has the features associated with the table. Now, we have a process that, based on vision, can both learn about stuff in the environment, it can also segment stuff in the environment. So we have a very, very primitive version of a symbolic representation. Right? It might just be A, B, C, D, but it's still like now we've separated the world into pieces, which is a super important part of AI. and this process, nowhere did it depend on vision being the sensor. It doesn't know anything about that, which means we can now do the same thing for other sensor types. So for instance, touch. This is a robot that has a biomimetic sensor fingertip, and we do the exact same algorithm and it starts touching stuff on the tabletop and it can build a model of the stuff it touches. So this is what the robot looked like when it was looking at the rubber duck and the plant. It's moving much more slowly than the simulated robot. But importantly, it regressed this model of the environment in about 5 minutes. like 5 minutes is sort of a workable amount of time. And it opens this question of, would it have actually helped it to have, say, a CAD model of a rubber duck? Probably in the case of rubber duck, the answer is yes. Would it have helped it to have a CAD model of a plant? I think it's much less clear, right? That like plants just don't have nicely digitized representations of what they look like. We know what individual plants look like, but we don't know what this plant looks like ahead of time. We did the same thing for ultrasound. So here you see the rubber duck has an ultrasound sensor and it's looking through jello for the rubber duck. And you see the shadow of the rubber duck, but actually ultrasound has these really interesting reflection properties. Sometimes you see multiple rubber ducks, and actually it figures out that even though it's seeing multiple images, it actually knows that there's one object out there that is where this feature density is centered. I love this particular example because we think of ultrasound in terms of their analogies to sensors, but actually there's no reason a robot needs to do that. It can just treat it as its own unique sensor type. This is a robot that only has a touch sensor, so we had to fix the duck in place. We had to fix the ball in place because right now we don't let them have dynamics. But none of this says they can't have dynamics. It's just like it's already hard to interpret. We definitely don't want to be in the business of interpreting models that are evolving in time explicitly. Okay, and so what I'm going to end with is this idea that active learning, the words make it sound like it's reinforcement learning. But early on, I said that these two things are distinct. You might be able to apply active learning, but they actually solve different problems. Reinforcement learning says, how should I act to maximize some reward that I've specified? Active learning says, how should I generate variation in my decision-making in order to improve learning models? So it's like the learning model, if you're willing to make that be part of your reward structure, then yeah, maybe you can do this. But now you'd be in the business of taking multiple layers of these Fourier transforms, like it's possible, but we just don't know how to do it. So I'm not going to talk about reinforcement learning. I have a whole gaggle of slides about reinforcement learning. But instead, what I'm going to do is skip to a conclusion slide, which is that this idea that decision-making can be tailored to learning needs, and that we might want to use like all the sort of mathematical stuff that we're good at as a way of guaranteeing properties of learning outcomes. We might want to guarantee that when I develop a perception model, that it satisfies certain bounds on how good it is, and that those bounds are have an explicit dependence on the data that I collected and maybe the way that I collected it. Like this seems to me like a bunch of theorem proving that could change how much we believe that if we send a robot out into the world, all these learning models, by the way, the perception models that I just showed you, the neural network always starts out uninitialized, right? There's no structure in the neural network except for its CVAE architecture. That is, like making promises about such a system has a lot of goodness. It has goodness in pretty applied areas. Like one of the things that I think is really interesting is that in robotic surgery, there's a lot of interest in understanding. So surgeons routinely find stuff that wasn't what they're there for. And when you talk to people who think about applying learning, the way that they think about this is, oh, I'm going to look at a bunch of images and there are tumors labeled. I know all of these images have tumors in them, and I'm going to regress models that tell me when there's a tumor. A completely different way that is more aligned with the way surgeons talk about it is that they're doing whatever they're doing, and then they just detect something that isn't usual, right? It's not a tumor yet. It's just like something that they're like, oh, what's that? And that's much closer to the process of the robot responding to the rubber duck. It's primarily responding to this entropy-rich part of the environment that it wants to go and do something with. And maybe we should want, in a safety-constrained setting, maybe we should want surgical robots that are busy drilling and doing stuff to my heart. Maybe we should want them to know, first of all, how to generate those predictions, but also be able to like satisfy safety guarantees, like if they're going to tell me that I have a tumor, I want them to be pretty sure. If they're going to tell the doctor that I might have a tumor, I want them to be able to say like what they mean by that. Like these are real things that are happening right now. And a lot of this comes down to what does it mean to certify, to mathematically certify machine learning algorithms. The last thing I'll say about that is that, like, I work a lot with Koopman operators. Other people here work with Koopman operators. People love Koopman operators because they are mathematically super well defined. And people don't like Koopman operators because they never work as well. And I think that the balance point here is that I would much rather have a lower performing machine learning representation if I can say something really precise about it. And that's going to be something that we have to get better at articulating. That if you want promises and guarantees, that's going to come at a performance cost, but that's okay. There are lots of settings where we accept that. All of robust control in the 70s and 80s was about that trade-off and about accepting that I would really like to not crash in exchange for not getting where I'm going as quickly as I might have otherwise. Okay, so I hope this was useful. Let me know what
Any questions?
Don't want me to be the only person up here.
Yeah.
So in system identification, we have this notion of that the system has to be sufficiently excited in order for it to get like a good model representation. How different is the concept of verbosity that you were talking about?
Yeah. Yeah, so in system identification, so first of all, this notion of persistent excitation is really connected to the fact that the parameters that are unknown are static. I understand everything I talked about here is fundamentally static as well, but there's like how generalizable is the idea of persistent excitation. The thing that where you can say something precise about it is in the case of static parameters. The other thing is that persistent excitation makes the most sense in local models, right? Where you can say the most about the value of persistent excitation is in places that are locally linear. And so if you want guarantees of convergence, particularly the exponential guarantees of convergence that persistent excitation provides, that's a local measure. And yeah, local measures of persistent excitation give you a local approximation of ergodicity for free in some sense. Weirdly, this is what happens in reinforcement learning, that there's all these techniques where people understand that what they want is a global property of coverage. And the way they implement it is by locally persistently exciting their policy everywhere in space. And it turns out that there's really good reasons why that cannot work. So you have like all of these benchmarks in reinforcement learning are hand-tuned to make it easier for the algorithms to function well on them. And so if you're just given something that you need to apply reinforcement learning to, you need to, my view is that you need to have a better model of how you're going to generate the excitations that provide coverage for your system. Yep.
You said that the robot knows its own dynamics.
Yeah.
Is that like that it knows its own like signal that it's giving to like the motors, or that it knows its own position?
So, okay, yeah, there's two components to this. First of all, it 100% knows its current state. Like it knows its own kinematics. Also, it knows the relationship between motor commands and changes in those states. So it can use those for purpose of planning. It does not have to simultaneously ask. So like, I think a really interesting example of this would be if you put the camera on the end of like some big soft body, big squishy octopus arm. Now it would have to both learn the physics of the camera as a sensor and learn the relationship between how the motors make the camera move in space and time. Also, it doesn't have dead reckoning anymore. It doesn't know where it is in space and time. Like there's a lot more that needs to be learned. That starts to make it feel more like a reinforcement learning problem, although you can frame each of those layers as its own distinctly defined learning that you have to do. That's one of the things actually Koopman models are really good for.
Is there anything interesting, or have you guys thought about how effects of noise in the observations would impact the learning process? So if it's like passive.
Yeah. So noise. There's a couple of things that are deeply unintuitive about ergodic control, and two of them that I'll call out here. One of them is noise actually locally always makes you more ergodic. And globally, it has the opposite effect. So like if you're trying to plan an ergodic trajectory and you make it worse through adding noise to the dynamics, then actually you do degrade the ergodicity relative to the global Fourier decomposition. Yet if you're at equilibrium and you add noise, then you improve your situation. And why the local and global are different from each other is intuitively clear, but it's not mathematically clear why they should be different. But this is related to the reinforcement learning and persistent excitation problem, that like you get local advantage, but you don't get global advantage. Secondly, so the ergodic metric is globally convex. That's super helpful to know. It helps you make promises about whether the optimization is going to give you a unique solution, et cetera, et cetera. If you have linear dynamics, you have a globally convex function subject to a linear constraint, you still have a globally convex problem, and yet trajectories are not unique. So how can that happen? It's because the space in which you are doing the global optimization is the space of distributions. And so the path, the way in which you go through that distribution is not uniquely defined, even if the distribution itself is uniquely defined. And this was like originally a thought experiment of thinking, well, if my distribution is a circle, then my linear dynamical system can go either way around the circle. And those are obviously two different solutions, yet they are both exactly ergodic to the same degree. And I know I have a globally convex function with linear constraints. But it turns out that it's this difference between, like, you have to really think about what space you're operating in, right? This is like not the way machine learning people tend to want to think about the world. Like they don't think about it as the topology of the space that you're operating in mattering to the interpretation of the behavior that you're generating. And by the way, it does practically lead to singularities. Like this issue, the reason we noticed it is that we found that we were running into singularities where the trajectory was at a saddle point, even though we knew that there were no saddle points. And it was because of the relationship between the space of distributions and the space of trajectories. Okay.
Thank you so much, Todd.